function for primitive ontologists.
So, normally when we're explaining to ourselves or others why we philosophers of physics spend so much time talking about quantum mechanics when it's obvious that we should really be talking about quantum field theory, we tell them some kind of story about how, well, it's a sort of warm-up exercise. We face a lot of the same problems, but in a more technical form, and we're confident that all the work we're doing now will be of great value later. So it's a real pleasure to be at a conference where people are actually talking about quantum field theory instead of quantum mechanics, but not me, because I don't know anything about quantum field theory. So this talk is going to be a warm-up exercise, and I hope that no one's strained anything this morning by sitting through a talk about quantum field theory without first doing a proper, gentle warm-up. All right, so it's a sort of truism now among philosophers of physics that a minimal criterion of adequacy for any approach to understanding quantum mechanics is that it should be able to make sense of the experiments that provide our evidence for believing the theory. That seems very good. That point is usually raised in order to set up the measurement problem. The problem of showing that the kinds of experiments we actually perform, using a walrus Chester to record the facts about the spin of some electron or something, that those kinds of experiments have determined outcomes. But of course there's another kind of problem besides the measurement problem that you need to solve if you're going to make sense of experiments, which is the macro object problem. You've got to be able to give an account in your giant zillion particle filter space of which physical states correspond to there being something like Chester, right? Some walrus or other, located somewhere, persisting through time, performing various actions. If not, formalism certainly isn't going to give you such macro objects for free. Although it's true that many approaches to solving the measurement problem include, or at least gesture at, a solution to the macro object problem as well. So this talk is going to be about a subset of solutions to the measurement problem that, along the way, solve the macro object problem in a particular fashion. So roughly speaking, there are two main ways to approach the macro object problem. You can find manifestos for each of these ways. One of them is by David Wallace. So under the more ambitious approach, look, the wave function is all there is in quantum mechanics. And of course, the wave function in quantum mechanics stands to the objects of classical mechanics as waves in optics stand to rays in optics. So we know there's some sort of way of going back and forth between descriptions of things of light, of optical situations in terms of waves and optical situations in terms of rays, but it's very complicated. And there's no precise correlate of a ray in a wave description. And the same sort of thing is what we should expect of the relationship between quantum mechanics and classical mechanics if we think the wave function is everything. So that makes the problem really hard, in part because you've got a sort of, you expect a sort of vagueness in the relation between the quantum picture and the classical picture, which is going to be difficult to explicate. We know that from the beginning. There's another kind of approach to thinking about quantum mechanics, which makes this problem easier in a sense, because you drop this analogy between quantum mechanics and classical mechanics and wave optics and ray optics, and you say, no, actually, although the founders of quantum mechanics forgot to write it down, there is within any quantum world a kind of pretty direct correlate of the classical world. So let's talk about primitive ontology approaches. And here I'm simplifying a little bit. So people who go under this name would point out to me that I was restricting in scope somewhat their picture. But just to simplify, let's do it this way. And say that an approach to understanding quantum mechanics is a primitive ontology approach if it associates with the history of any quantum particle a subset of points in the space-time in which that particle lives. So in the Bohmian case, you actually get a world body. And in certain versions of the GRW approach, you get a sort of pixelated world body. And now it's going to be easier to make a connection between what it says in our lab book about Chester's behavior and what sort of things we get in solutions to our theory. I mean, sometimes we're going to have a sort of cloud of roguelikes that's walrus-shaped, or a cloud of points that's walrus-shaped, the way you go. So that's a sort of attraction of this way of thinking about things. But, of course, these primitive ontology approaches are fundamentally dualistic. On the one hand, you have the wave function, and on the other hand, you have these particle histories. And in talking about the measurement problem or the macro-object problem, advocates of the primitive ontology approach always emphasize how simple and straightforward and straight shooting it is, because you get direct correlates of classical objects in the quantum world. But they tend not to say very much about what's going on with the wave function, how it works, and what it does. So most of this talk is just going to be developing some options for thinking about the wave function if you're a primitive ontologist. I'd like to say that this is just a warm-up exercise for people who would rather take the wave function to be everything, but as we'll see, a lot of the options that are available to the primitive ontologist wouldn't look very interesting at all outside that context. Okay, so I'm going to run quickly through some options for primitive ontologists who are Bohmians, and then hopefully spend some more time talking about a special case of the GRW approach, which encompasses this relativistic collapse model recently developed by Tumulka. So there'll be something neighboring quantum field theory, although we won't quite. Okay, so let's think about how Bohm works. Say we have n particles without spin. They all live on a line. So we have this classical configuration space, Q, which just a point there just corresponds to specifying the position of each of the particles. A wave function is, at least roughly speaking, a complex valued function on the configuration space. Schrodinger's equation governs the evolution of this. And then we just need one further object, which is, in Bohmian mechanics, the particles always have determinate positions. Right? So in order to specify an instantaneous state, we have to specify not just a wave function, but a point in the configuration space. And then Bohm's equation of motion tells us, if there you are at the beginning, and that's your wave function, then you move along some particular curve. Another way of putting that is, for any point you could be at, if you know the history of the wave function, then you know which curve it will go on. Another way of putting that is to say that for any point you could be at, it tells you, if you know the wave function, you know your velocity in this space at that time. And just giving you all those velocities at every point gives you these curves. Another way of putting that is to say that we have this most abstract way of thinking of it. We have a gizmo, which is the Bohmian dynamics. Depends on the Hamiltonian introducing the force. And what it does is, it maps a solution to Schrodinger's equation to a time-dependent vector field on Q. Okay, so if you say at each t what the wave function, it tells you what the corresponding velocity field is at that time, and then you integrate out to get these curves. We'll leave that in a little bit. We'll come back to it. The wave function has one more role in Bohmian mechanics, which is to tell you about the probabilities. Roughly speaking, it tells you which configurations of the particles are typical at a given time, and which ones are odd or surprising at that time. So you can see how people would feel like the interpretation of the particle part of this theory is straightforward. The interpretation of the probabilities is sort of, as always, a little mysterious. But then there's this third thing we have to worry about. How should we think of the wave function? So the first thing you would notice is it plays a role in the laws of motion for the particles. So you think, okay, well, I sort of know what a law of motion looks like in classical mechanics. I'm used to that, so I can think, F equals ma, what do I have? Well, I've got some things, the particles, or fields in other classical theories. I've also got some properties like mass and so on. And I've also got a law, the whole thing. And so those are the three basic options that people have hit upon for interpreting the wave function in primitive ontology approaches. We could say the wave function is like a property, it's like a thing, it's like a law. So start out with the most straightforward thing. It's like a thing. So notice that if we only have one particle living on a line, then our configuration space is just the line. And this is just a function from the line to the complex number. So you think, ah, it looks like a field on physical space, right? My physical space is just one dimensional. Now, obviously, that's not true if I let n be greater than 1, so I'll have to generalize a little bit. But there are two obvious ways of doing that. So, one of them is emphasized by David Albert. Think of a wave function as a field on configuration space, not on physical space. The sorts of physical objects that wave functions are plainly fields, which is to say that they are sort of objects whose states one specifies by specifying the values of subset of numbers of each point in space in which they live. The sort of objects whose state one specifies by specifying the values of two numbers, blah, blah, blah. Okay. So we're going to think, okay, yeah, when n is greater than 1, the particles all live on a single line, but the space on which the wave function is defined is bigger than just a single line. So it looks like a field, but it's defined on some space other than the ordinary physical space that we use. That's one way of doing it. But there are plainly other options. So you could instead generalize the notion of a field, right, and say, in classical theories, a field is an assignment of properties to each point of physical space. Albert wants us to think, okay, well, then the space that's real isn't physical space that we're used to, but some larger object. And then we still think of wave functions assigning properties to points. The other option is to say, we should generalize in another direction and think of fields as assignments of properties to n-tuple points. And then we can just stick with physical space as the space in which the wave function lives on as a generalized field or a multi-field or something like that. Right, and then, you can go through the advantages and disadvantages. So one problem that arises here is that this is only, roughly speaking, a complex value function on configuration space, the wave function, so you might worry a little bit about how things look if you take that into account. You might also notice that fields, as physically real objects, were introduced into physics in the 19th century because they played certain causal roles. They could store energy, they were acted and reacted upon, and so on. And the wave function doesn't look like that. So there's a question whether we have a mere mathematical analogy or anything deep enough here to say it's worthwhile in talking about a field. If you were choosing, I think, between the Albert way of doing things and the multi-field way of doing things, I think you'd also have to worry a little bit about whether, we had to generalize the notion of a classical field. Is it better to generalize it by thinking that, we don't actually live in three-dimensional space, we live in 3 zillion dimensional space, and any illusion that we have to the contrary has to be explained away, as Albert sort of says in this quote here? Or should we just revise this technical notion of field and let it take multiple arguments? It seems to me that that's a disadvantage of the Albert approach. It's sort of lovely because it's so mind-boggling, but it seems like he's driven to it because plainly these things have to be fields of the sort we're used to. It just seems, hastily taking on a very interesting but very difficult problem, namely explaining away the illusion that we live in three-dimensional space. All right. Let's think about the possibilities for thinking of the wave function as a property. So I have all kinds of dispositional properties, such as cowardice. And when you think about my cowardice, right, one of the things it's telling you is how fast I would move if I found myself in various situations. And also the direction in which I would move. So we can think of the wave function as doing exactly the same kind of job. Right? If we fix the wave function, then for every way the particles could be disposed in physical space, there's a point in the configuration space of the wave function via the Bohmian dynamics tells them how fast to move. So why not just think of the wave function as an extremely complicated dispositional property of the entire system of particles? Well, one worry that immediately arises is that telling the particles how fast to move is only half the job of the wave function in Bohmian mechanics. The other half is assigning probabilities. So, in particular, two wave functions can agree about how fast the particles are moving, but disagree about which configurations are typical. And indeed, this is true even if you look at solutions to the Schrödinger equation. Two solutions to the Schrödinger equation could induce the same kind of vector field on the configuration space and yet disagree about the probabilities. This is particularly clear in the example of particle in a box. An example always unpleasant for Bohmians to consider because things are weird for them with this very simple physical system. In that case, the dynamics give you, the Bohmian dynamics is very simple. If you consider energy eigenstates of a particle in a box, the particles just sit there forever. None of them ever move, no matter what the energy is. So you're like telling people, don't put your hand in that box. The particle will take your hand right off. It's got so much energy, but in fact it's just sitting there until you put your hand in it. Right? So that's maybe slightly embarrassing, but here the point is a technical one. That these energy eigenstates disagree about the probabilities for where to find the particles, but they all agree that the particles just sit there forever. However, you might wonder, I should say, if you were me, you might wonder about whether the following proposition were true. Sounds true to me. Whereas I would say, I asked Shelley Goldstein whether it looked true. He said, yeah, it looked like it might be true. So I think I was merely wondering about Goldstein was conjecture, because he's in a very different epistemic state than I am with respect to mathematical questions. So you might conjecture, if you were Goldstein, that a generic solution to Schrodinger's equation for a fixed Hamiltonian is determined by the time-dependent vector field it induces on the configuration space via the Bohmian law. So it's not true, just an example that showed it isn't true always. But Goldstein conjectures that it's true for generic states. So it's only for very special solutions of the Schrodinger equation that this isn't going to be true. In that case, you can get away with just thinking of the wave function as the complicated dispositional property telling you about the velocities particles would move at if they found themselves in various situations. And recover the probabilities from that, except in special cases where you say probabilities aren't defined. A feature of doing this is that you'll end up saying that there are non-trivially distinct wave functions that correspond to the same physical situation. And of the options we're going to talk about, this is the only proposal that has this feature. Right? So many philosophers of physics, when they hear talks like that, they think, but these are just metaphysical questions and probably there's nothing at base going on. But here's a sort of physical difference that hangs on which of these interpretive options you choose. Right. Anyway, so I mean, obviously there are all kinds of words about this approach. So a lot of people don't like bare dispositions, which is what these things would be. Right? They're not supervening on other physical properties. We're not really used to infinite dimensional determinable properties. Right? So that might seem weird, like the wave function is chosen from an infinite dimensional space. And many people don't like holistic properties for systems of particles. We're certainly not used to that, although it's hard to avoid holism sooner or later. How am I doing on time? Did I start on time?
Yeah, no, you started 5 minutes late, and you have about 15
Good.
on the schedule.
Right. Okay, so let's quickly talk about the third option, which is, in a way, the weirdest and most interesting one. So think of the wave function as a law. So begin with the observation that in classical mechanics, we often start out by writing down the configuration space of the phase space for a system, and then saying what the Hamiltonian is. Right? This is a highbrow way of doing Newtonian mechanics. The Hamiltonian is just telling you what the forces are. Something you could have said. Otherwise, but this gives you a nice general and abstract way of writing things down. But it's clear when you do this, the Hamiltonian is a function from the phase space to the real numbers. It's like a field on phase space. It acts on the particles in some sense, but isn't acted on by them. And so in some ways, it's looking analogous to the wave function. But nobody thinks that almost nobody thinks that it's a field on some physically real space. Right? People think, okay, the Hamiltonian is really part of the gnomic structure in this theory. It's not a field, it's not a property. Well, it is a sort of property, but it's part of the gnomic. Specifying the Hamiltonian is part of specifying the gnomic structure of the theory. So there's a suggestion that we should think of the wave function the same way. Broadly speaking, the wave function is particle laws. It tells particles how to move. Okay? So after having fixed the type of system that we're talking about, its composition, what the forces are, we still haven't quite fixed the laws because we haven't really told the particles how to move yet. So we also specify the wave function. So this is a further part of the laws. It's a little mind-boggling. And it's obviously very strange. It runs counter to our normal intuitions in a couple of ways. One thing is, it looks a lot more like the kind of thing you specify when you specify the initial conditions than when you specify the laws. Because presumably for physically realistic wave functions, the wave function is incredibly complex. Right? We're used to thinking of specifying the laws as specifying something very simple. Also, for physically realistic systems, the wave function is time dependent in an interesting way. And we don't normally think of the laws as being time dependent. So that seems like two strikes against this approach. But there's a very valiant counterattack being mounted by its advocates, who hope to be able to get rid of both of these flaws in one stroke by showing that if you're considering the quantum theory of the entire universe, including its gravitational aspects, it would turn out that the wave function was both incredibly simple and time independent, and that these other features that we identified arise only when we're writing down effective theories for subsystems. So, I mean, if true, that would be fantastic, and would make this view much more plausible. Okay, so what's the score at this point? We had three possibilities, right? Object, property, law. This one split into two species. One of them was sort of down to earth, and the other one was sort of wild and brought with it difficult problems. This one's sort of metaphysically not entirely attractive and brings with it an interesting technical problem. This one's metaphysically highly unattractive unless some very interesting technical conjectures are true. So the score is, the boring version of this is the easiest and least interesting way to go. Take the configuration space to be something like a generalized field on physical space. And the other ones are all more interesting, but bring with them very hard to think problems. Okay, there we go. That's the first half. So now let's talk about GRW. So the idea in GRW, I mean, I know almost everybody here probably already knows more about this than I do, is that normally the state undergoes Schrödinger evolution, the kind we know and love from other versions of quantum mechanics. But occasionally, this is interrupted by a collapse event in which the wave function suddenly discontinuously changes. Each collapse event is associated with a label corresponding to one of the particles that we're talking about. And its net effect is to suppress macroscopic superpositions that involve that particle. So these events are very rare in the history of any given particle, but because there are so many particles in here, all of which are highly correlated with one another, as long as one of them, as long as in any given short period of time, one of them is undergoing a GRW collapse, the whole thing isn't going to enter macroscopic superposition. Or it's as if we could say that it isn't. Okay, so we want to consider a version of GRW in which you get pixelated versions of particle world lines. And so the way we do it is we take a history of the wave function, evolving Schrödinger, evolving collapse, Schrödinger collapse, right? And then we label in space-time, we put a dot for each of those collapse events, corresponding to the particle label and the point in space about which the collapse was centered. And in this way, we go from a history of the wave function to a pixelated version of the world lines of the end particles. Whenever, one important thing is, whenever a collapse occurs to a given particle, its next collapse will be in the causal future of its predecessor. So it really does make sense to think of them as world lines, pixelated versions. Okay. And here's how it looks like when you write down a theory. So unlike, this is a theory that looks a lot like a classical theory. You write down the initial data, you solve the differential equations, you get the whole picture. But the GRW thing is a stochastic theory. So they're these random events. And so you can't do something like that because specifying the initial data doesn't specify what's going to happen. So instead what you get is an algorithm. The input for the algorithm is the wave function at some instant of time. It erases itself. The wave function at some instant of time. And if you're doing the relativistic version, also the last flashes that occur, flashes of the label, what we call the dots. The last flashes that occur right before that instant of time. And the output is a probability distribution over possible future patterns of flashing. Also, rule that tells you if you've got the input and you say, okay, now I'm pretending I ran the algorithm and I got some particular pattern of flashes. Now I have a rule that tells me if I pick some later instant of time, that there's a sort of effective wave function I could write down there. Would be the wave function after those flashes, in the sense that the probability distribution that this guy gives you over future flashes future to him is the same probability distribution that the original guy gave you over flashes future to that guy, conditional on the pattern of flashes that you're taking as actual there. So that's how the algorithm works. Okay, we've already said what a flashy TRW world, we're going to have to say, we're going to definitely have to specify the primitive ontology in order to specify the world, namely the pattern of flashes that occur. And we're also going to have to specify everything about the wave function of that world, because those are the two aspects of our ontology. That second part is a little subtle, it turns out. Specifying everything about the wave function of a TRW world. We'll see that there's various ways. This is at the technical level before we get to interpretation. Various ways to say what it would mean to specify all the wave function facts of the TRW world. So let's start with the non-relativistic case. So the non-relativistic case, everything's pretty nice. Right? We've got some countable number of flash events, which are time-ordered. Right? So we just write down all the times at which they occur. And we have a rule that tells us if there's a flash, what the wave function is going to be right after that. So associated with each flash, we've got an effective wave function for after that flash. Okay? Now that doesn't seem like it quite gives us everything about the wave function of that world. Right? We would normally think there are wave function facts at times in between the flashes. So now we've got to say something more about the wave function to fill in the story to make it look like we've told ourselves everything about the wave function of the world. There are three basic ways to do this iteration. I mean, there are probably more, but these ones are variants on them come up. There's a standard approach in which you just make basically, you make a global in time wave function by stitching together the ones associated with the flashes by interpolating by Schrödinger evolution in between. So if I know what this guy is, then I say, I know what the effective wave function is at this flash, then I say, okay, to the future of that flash, the wave function is given by Schrödinger evolving this guy, until you get up to the time of the next flash, and then it jumps. Okay? So that tells you what it is then, and then you do the same thing. Okay, so you make a single defined on all times wave function that evolves sort of the way you would picture, given the general idea of the DRW, that the Schrödinger evolution is interrupted by these collapse events. So you can see why I'm calling this the standard approach. It's the approach that's implicit in most discussions of the classical theory. But there are two variants on this, which I'm calling no collapse 1 and no collapse 2. In no collapse 1, we suppose that the world is temporally finite towards the past. Okay, so maybe we're working in well, we're just cutting off space-time at some finite time in the past to give us an analog of what we think things are like in general theory. And then you just pick a time. I mean, there may even be a boundary back here. You can say, oh, that's the creation, right? The Big Bang or whatever. I know what the wave function is at that ideal boundary. And then you Schrödinger evolve that for all time. And you say, okay, that's what the wave function would have been at all times if there had been no flashes. Now I know that there were some flashes, and I know I've got this far. I know there were some flashes, and I know they're going to be some in the future. But in order to calculate what they are in the future, I just say, I take the wave function that would have been if there had never been any flashes, conditionalize on the pattern that's happened up to this time, and then I got the probability distribution of the future ones. So there's no collapse in this picture. There's a single wave function defined at all time that involves in accord with Schrödinger evolution at all times. But it looks like we only get off the ground because there's a time before any of the flashes happen. Or, in some variants, right after the first flash for each particle happen. But anyway, it only works if... This is a very nice picture, but it only works if past is temporally is finite, as far as I can tell. Here's a much uglier alternative. Let's first of all keep thinking about the temporally finite past example. So we start out, we've got the wave function at the beginning of time, and we can short order evolve it and get the wave function at all times. So that gives us one wave function, we'll call size of 0, defined at all times. Then we roll on for a while, and then there's some flashes. All right, so now, so there should be one flash. Right? So now I get a new wave function, right, defined at that time, but I can also Schrodinger evolve that to all times past and future and get a second wave function defined at all times. And I can just keep doing this. Whenever there's a flash, I write down the effective wave function. I use the Schrodinger evolution to evolve it backwards and forwards to get a new wave function defined at all times. And in this way, I get a countable family of wave functions defined at all times. Okay. This is a strange thing to do, but it's certainly one way to go. All right. So how should we think of these three technical options for writing down the wave function facts at each time? How do they look if we ask, okay, well, what is the wave function really? So it looks like the object approach, the multi-field approach, will be well suited for any of these three. Although, of course, under no collapse 2, facts about distant flashes are encoded in the wave function at each time. Right? So if I ask about all the wave function facts at this time, those will include all the facts about future flashes away, the ones that are encoded in the later members of this sequence of wave functions. So that's weird, but that's what happens if you represent wave functions that way and you think of the wave function as a multi-field. But in light of that fact that's just noted, thinking of a wave function as a dispositional property, the disposition of a flash or something like that, looks like quite unattractive when combining with no collapse 2. Because if the wave function facts already tell me everything about where future flashes are, it seems silly to think of the wave function as encoding the disposition of flash. I've got all the actual facts about flashes.
You're getting close to the normal time, but I think we can.
Yeah. Is that right? I thought he had.
We're going to 12:15.
So I was figuring you were going to stop at 8 on 40 for your talk. But that's okay.
Just keep it. All right. It won't be that time. But 45 minutes.
Yeah.
And so we started at 5 after.
I'm sorry.
And so I go to
So that'd be in the middle. Yeah.
10.
So I get in a sense.
Yeah, sorry.
15 minutes. Okay. Excellent.
Last time doing that calculation.
Yeah. All right. Okay, look. The law, treating the wave function as a law doesn't seem to go very well with the standard approach. Under the standard approach, remember, there are these stochastic events, the wave function collapses, and the wave function is also temporally evolving. It seems really going too far to think of the laws as stochastically evolving. Or, I should be more careful, that's a very interesting view, but it doesn't seem to be forced upon us by anything about quantum mechanics. We wouldn't have thought. Okay. I mean, since I got so much time, have a side here about Tumulka, who's the great engine behind many of the recent developments in GRW, is that he appears to think of the flashes and the wave function as being on a very uneven footing ontologically. Although it's part of the official view that primitive ontology doesn't exhaust ontology, the wave function is part of the ontology. Nonetheless, the only thing the wave function is doing for you is giving you a probability distribution over future flashes. And so if there's two different mathematical objects that encode the same probability distribution, then you should really think of them as being exactly the same. That's the idea is something like the basic laws of the theory concern the probability of flash histories, and the wave function is our way of formulating such laws. But mere differences in formulation don't correspond to ontological differences. I mean, and this kind of lack of interest in what look like differences between wave functions, I think, really pushes you towards the law way of thinking about things in a way. Okay. So let's talk a little bit about the relativistic case, which is by far the most interesting one. So it's a very special model that Tumulka has written down. It only treats n free massive particles. Okay, the n has to be fixed, right? So there's no accretion and annihilation. They have to be free because the basic equation he's using doesn't work if there's interactions. And they have to be massive because they've always got to be, given a flash, the next flash has to be inside the next light, inside the light limit. It won't work if you try to let them happen on the light. And there are probably also interesting restrictions to the kinds of spacetimes that you can set this theory in as well. Nonetheless, it's amazingly interesting to see what it looks like to write down a relativistic model of collapse that doesn't in any way require breaking Lorentz in its dynamics. Okay, so here's how it works. So the wave function is going to assign, oh yeah, these are particles with spin. So the wave function is going to assign like little spin guys to n tuples of space-time points. And the basic dynamical equation is kind of weird. It's the multi-time Dirac equation. What's weird about it is, in order to specify, here's one way to specify initial data for the multi-time Dirac equation that will give you the state at all past times and all future times. You could, remember the wave function of this form, you could, for each n tuple of points on some Cauchy surface, specify the value of the field there, and then that gives you value at all times past and future. But there are other alternatives. There's a point on that thing. Here's a hyperboloid in the past light code. So these are points at some constant proper time in the past of this point. Specifying the value of the field for every n tuple of points lying on this hyperboloid will also specify the field globally. Even weirder, we could pick n different Cauchy surfaces or hyperboloids or other initial data surfaces and write down the value of the field for all the n tuples of points where the first guy is chosen from this hypersurface and the second guy is chosen from this hypersurface and so on. Okay, so you don't need to have all the points drawn from the same initial data surface. Very cool feature of this equation. And it's not so surprising that you can't generalize it to allow interactions. Okay. So maybe, should I just say maybe one thing about what the rule for collapse looks like? The idea is, I got Minkowski spacetime. I've got some flashes. I've got the wave function defined at some time. Here's this particle that I'm interested in. I know that he's going to have a flash to the future of his hypersurface, and I want to find out where in spacetime that flash is. This is what I do. Just as in GRW, I sort of have a constant probability of collapse associated, constant in time probability of collapse associated with each particle. I do the same thing here, but now with proper time. So I consider all the possible positive values of proper time. I'm assigning equal weight to each of them, and so I expect there's some time that's like 3 times 10 to the 6th years or something, in which I expect a collapse for any given particle. So I find the value of proper time for which this guy has a collapse event. So that gives me, then I look at the points lying on the surface, that distance in proper time from the point of his last collapse. Then I use the wave function to give me a probability distribution over this thing to decide where in space the collapse takes place. And now I've got a new collapse. I do that for everybody at once, and then my algorithm for writing down the new effective wave function exploits the fact that the initial value problem is well posed, even if the values that are all being chosen from different sources. So that's the idea. Okay, so there are 3 strategies here for representing the wave function facts in addition to the flash facts. Strategy 1 would involve doing something like assigning a wave function to each acceptable initial data surface in Minkowski spacetime, and somehow there's a very, very complicated meshing problem because these two initial data surfaces cut past each other, right? So there are some flashes in the region between them. So it's we sort of know, if we've got an initial data surface, we know what the wave function is, we know what the flashes are just in between them, then we sort of know how to update. But now we've got to do this for every family of hypersurfaces in some very complicated way. So I don't myself know exactly what the conditions you'd want to write down here are for the mesh. So what was the standard, straightforward, obviously most interesting way to do things in the classical case becomes extremely subtle, I believe, in the Minkowski spacetime. So it's not so obvious what the analog of the standard approach is in this case, but I think it'd be interesting to try to work with. Strategy 2, well, if space-time is finite towards the past, we can do the same kind of trick we did before. We can posit a first generation of flashes, one for each particle, put a hypersurface in the future of that, and say what the wave function is at this time. Then use the Dirac equation to evolve it to be everywhere, and just build the occurrence of future flashes into the algorithm rather than into the wave function. This is the direct analog of no collapse 1 from Coase theorem. But of course, if space-time isn't finite towards the past, this kind of picture doesn't work. There is no first generation of flashes. And the remaining option is no collapse 2, this horrible one, where you had a whole family of wave functions, each of which was defined on all of space-time. And of course, you could do the same thing here, and it would look just as horrible. So, in this case, you'll go, okay, for every way of dividing the flashes up into generations, one from each particle, I get a wave function defined on all of space-time that tells me about the probability distribution of future flashes to that family, future to that family. And again, there'll be a meshing. Although in this case, it's much better understood what it was. Okay, is this theory local or non-local? So, I mean, you sort of want it to be non-local. Right? Nobody wants their quantum theory to be local. It'd be terrible. And so, the people who've been developing this approach say, like, okay, look, roughly speaking, a GRW theory is local if, in order to predict whether a given particle will flash at a given spacetime point, once you've conditionalized on the physical state in the past light cone of that spacetime point, there's no point in conditionalizing on information at space-like separator regions. So the idea is, say I've got these two particles, and I know that their positions are highly correlated. And I want to know whether one of them is going to flash here. So I look at the past light cone. And in the past light cone, I find flashes of each particle. Because it's so unlikely that two will ever flash at the same time, I mean, there's no clear pattern about this, but it's consistent with the fact that their positions are highly correlated. You never find them very far apart, close in time. I want to know whether the guy's going to flash here. It seems like the theory is local if I know all the facts about the past light cone, then I'm in a position to make a good prediction. And so obviously, because it's a stochastic theory, it's not deterministic, I can't say with certainty what's going to happen up there, but there's no point looking outside the past light cone to get more information. But that can't be true in a theory like this, because if I find out that the other particle flashes over here, then I can be pretty sure my guy isn't going to flash anywhere near here. Because their positions are highly correlated. I should have drawn that dot further away. That's the picture. And so here's Moblin in his commentary on Tumulka's model. It cannot be that full information about the past light cone of an event is maximal information for physical predictions. But what will happen at the event? By looking outside the past light cone, one can improve one's bets about what happens at the apex. Belot proved that no empirically adequate theory can avoid this result. And in Tumulka's discussion of locality and non-locality, he does things basically in direct parallel with the way Bogman's setting things up here. So the idea is fixing the primitive ontology is telling me about the pattern of flashes in the past life. Fixing the wave function part of the ontology is telling me what the correct algorithm is for predicting whether there'll be a flash here. And when you set things up that way, you know that finding out information about distant flashes will give you extra information about the probabilities of the flashes being used. So this looks like it might be the right way to proceed if you think of the wave function as being a law. Although it's not, because the view requires fleshing out, it's not totally clear to me whether that's right or not. But at least it does look like a plausible way to work if you think of the wave function as well. What happens if you think of the wave function some other way? So say you think of it as a multi-phase. Then is the theory local or non-local? Well, it depends on which of these three approaches we use to representing wave function facts. It seems, no matter what the pattern of flashes is back here, it seems plausible to me that for generic patterns of flashes that you can find in the past light count, that there will be some space-like hyperboloid that's to the future of all of them. Okay, so that might not happen. You could have flashes, because if it's temporally infinite to the past, you could have flashes piling up near the edge of the light cone, and that will prevent you from putting a hyperboloid like this, but that's the only kind of thing that would prevent it from happening. That seems unlikely. So let's just assume that we're interested in a case where we can pick a constant proper time hyperboloid like this that's to the future of all the past flashes of the light. Then we take the wave function to be the wave function our theory gives us for this. If we're thinking about the wave function using either of the first two strategies we were just discussing, then that's all of the information about the wave function in the past light. We fixed all of it by fixing this gap. And so the theory will be non-local because it will still be valuable up here. But under strategy 3, this won't be true. Under strategy 3, remember it's the analog of the one where we have a wave function defined on all of space-time corresponding to each flash event. So by just looking at this family of wave functions, we can say where and when the flash events occur. So under strategy 3, on this, corresponding to this hyperboloid, there's a whole family of wave functions. And that family as a whole contains information about where all the future flashes are. So in particular, it tells you whether there's going to be a flash event or not. There's no point looking at that. So the theory becomes local under this interpretation. Now, that's not very surprising because this is an account in which there's backwards causation. When the flash happens here, the fact that there's a flash here is reflected in wave function facts in the distant past. And if we're thinking of the primitive ontology as calling the shots, then we're likely to think, okay, the flash is, the real thing, and its occurrence caused there to be this feature in the wave function in the past. So I think that's right. But so it's not that I want to advocate this way of understanding the wave function and say, oh look, it's great, we can have a local theory. It's a crazy local theory. Nobody would want to advocate it. But the fact that the theory comes out as local, when the wave function is understood in this way, shows that the kind of characterization of locality that Rotman and Tumulka are employing has causal notions written into them. It would be difficult to give, I'm sorry, actually that's the wrong thing to say. What it shows is our intuitive notion of locality has implicit in it causal notions which aren't reflected in their formulation. So the theory counts as local under their criterion, even though it's obviously not local in the intuitive sense they meant to get at. So it's going to be hard to characterize locality using the kinds of materials that they were using. Second thing to say is that the theory is very bizarre, as I've understood under strategy 3, but strategy 3 actually is what's suggested when you first read Tumulka's papers. It seems like that is, in fact, how he's representing the wave function, at least in the early versions of the theory. So there's a sense in which strategy 3 is much better motivated, I think. I mean, not because of that historical fact, but because it is the natural way to represent the wave function in the kind of theory that he's written down. So it's not, although I don't want to stand up for it and claim it's a great way to do things, it is a little less strange and unmotivated. But the main conclusion of the talk is that, as will be obvious in my case at least, that we're all still primitive ontologists in the non-technical sense when talking about the wave function. Thanks.
Any questions?
You presented these three options of object, property, and law. It seemed to me as though they were mutually exclusive. Do you really feel that way?
I guess I did, but I'd be interested to hear. I mean, I definitely don't think they're exhaustive. And so that's sort of that's what I thought the first question. They strike me as being mutually exclusive, but I'd be interested in hearing more about how to
It
rank
seems
them.
that there's sufficient fuzziness around the edges of each of them so that they could wash into one another.
Yeah. Okay. Yeah. No, I think
But,
that. I don't feel like I really understand how the law of one is supposed to work, so it would be unwise of me to say that it's clearly distinct from the other one.
But also, a question about the flashes in the case of finite time in the background.
Yeah.
Let's forget about the limitations on Tumulka's present papers and assume that eventually we can extend this approach to real space-time, which we currently tend to believe
Right.
has only existed for 13.7
Right.
years.
Right.
It's not clear to me that in a case like that there would be first flashes, because even though the time is finite, the frequency of flashes may intensify as you go back into the cataclysmic times. Towards the Big Bang.
Yeah. So I should say, I mean, when I said, Tumulka, in his most thorough and eye-dotting presentation, restricts the theorems to being set in McKesson spacetime. But in his other papers, he claims with, I think, considerable plausibility that the theory can be set in many general relativistic spacetimes. I mean, what you need is that the initial value problem for the multi-time Dirac equation be well posed for some interesting, some non-trivial family of initial data synthesis. And it seems it seems plausible that will be true in standard cosmological models and so on. So, I mean, there's nothing stopping him from putting in a Big Bang thing, and that is sort of, one way that Tumulka sometimes talks is like, oh yeah, we'll just put the first flashes of the Big Bang. But it's not clear to me what geometrically that means. At other times, maybe it's Moglen who says like, oh, we'll just put them very shortly after the Big Bang. But the rule for distributing the first generation of flashes isn't spelled out, and it can't be in Tumulka's model in the first. And so it's a weird feature of this relativistic model that requires the seed flashes, the first generation ones, in order to get off the ground. I'll say one more thing about the probabilities. Yeah, so that's one possibility that conditions back here could force the flashes to happen more often. I mean, another possibility is say the universe is short-lived, right? Then we don't necessarily expect there to be a flash subsequent to the first one for every particle. Then it becomes weird for us to start talking about probabilities. So, I mean, there's some tension between thinking about probabilities as supervening on actual events and taking this theory seriously if you're considering temporally short universes.
Yeah, I mean, very quick comment first about kind of mentioning it's a rival route here. I don't want to drag us into a knowledge to them. Perhaps just to flag quickly that I think it would be dangerous for people who push the primitive ontology line to think that once we've got the world lines, everything's fine and all this is just world lines and all the shapes. I mean, the story about how we go from some friendly point particle story to the macroscopic it seems to be going to have vagueness and problematicness and
Yes.
all sorts of trouble along with there.
Yeah.
And in a sense, it's the way I characterise the kind of alternative routes to take that one down. I mean, that's just
Right, exactly. And I think they would agree and say, like, yeah, but we've got this foundation and then a bunch of swamp on top of it, but
yeah,
they won't
they
have different
differences. They want there to be a foundation that's sort of spatiotemporal and reasonably well behaved, which is I think more than reasonable. It was a standard comment. I mean, this is going to think about the property line forward, and I mean, Goldstein himself has said things a little bit like this, but we just to push it. I mean, I traditionally would think of universities as two things, Oxford and if it isn't Oxford. Many of my colleagues who are quite narcissistic people would probably be quite attracted to the idea that actually there's only an Oxford, and that where we thought there was stuff that's not Oxford, that's just the dispositional property of Oxford.
Right.
Now it feels like, I mean, what's the one thing you could say that is the way Oxford's rated? It kind of feels like, and I know we're not positivists anymore, etc., but it kind of feels like in taking that line we're doing something worse than just taking a slightly physically unattractive or slightly arbitrary line. It kind of feels as if in saying, well, all this stuff is just property of Oxford, was slightly using the word property in a funny way we didn't have in mind in the first place.
So are you worried about a sort of dispositions all the way down work?
I'm kind of worried about
is it something?
I'm kind of worried about the fact that if there's something I don't like in the through my ontology, I can just call it a property. Maybe I don't like George Bush. Okay, so this is the George Bush. It's just a certain dispositional property of everyone in the universe who isn't George Bush. And something feels wrong there. Something feels like it's not just in quantum metaphysics, it's misusing language.
Yeah, I guess I didn't see that, but I agree it's a very strange view. I mean, I think it's worth thinking about this one because a lot of people are like, some people's first reaction when pressed to say what the wave function is to say, it's just a property. Right, so Brad Montauk is the person I can think of who is defending this view of print. It's a sort of view, I believe, where there's a giant family of possible properties the universe could have parameterized by a Hilbert space. And at each time, the universe has one of these properties. And that's all there is to say about what's going on. And so, I mean, one thing that seems strange about that is the Hilbert space itself has all these symmetries. So it seems like all these properties are really the same in some way. At qualitative level, but obviously we don't think that about distinct Hilbert spaces. So, I mean, I think this is one point in the dialectic where I think it is worth thinking about whether this can be carried over to a wave function as all a way of thinking, or whether it's a total non-starter if you get rid of the particles.
So I guess one way of putting my spine here is, once one starts being quite this liberal with my property, I start to lose my grip on what it means. And I start to lose my grip on what we've actually said when we say that the wave function isn't an ontic entity, it's just property of itself.
See, the cowardice thing, it's so central to my life that it just seems like what could be more clear than saying that the guy, each of the, some of them are brave and some of them are cowards, and you say how they're arranged, and that the wave function tells you how they're arranged.
I'm not saying I don't get it there. I'm confident. I mean, leaving aside the totally unfair things to claim about yourself, sure, I'm not denying there isn't some philosophically salient notion of property, and that we can't claim relevant roles. I'm not even running a well, they can't be their line or anything like that. I'm just kind of saying that I'm not so confident that this is if we think we've got our grip of what properties are from this kind of example, the move we made is so profound and radical from situations like that. I lose my confidence we get it. I kind of feel Wittgenstein saying it's great.
Yeah, so I mean, this is another place where people might want to think about, like, is it okay to think of the electromagnetic field? How would that be?
Well, they think it's an Oxford's property. Again, what are the rules?
Right. Yes, I guess a question for people to take up. But.
So I had just a clarificatory question about locality, not on any particular reading, but just sort of in the Tumulka model. So you said if you have a flash of a point, then that will determine the probability distribution on the surface at some proper time in the future. So you have the wave function defined over that hyperbola that's confined within the future lifetime. And I mean, it just struck me, I was worried about whether this is compatible with theorems by Hagerfeld and things that David has shown about it. If you have a particle confined to a region of compact support, then it in some sense spreads outside the light from the so I'm not sure if that's something that's incompatible with Tumulka's model, or there's some assumption that the theorems that use. Or perhaps I misunderstood the theorem.
So we're not, the wave function is always going to be non-compact support.
Okay, so you can the flash doesn't mean it's...
No. So, I mean, like in ordinary GRW, you make the tails small, but they're still there. And so you don't get the kind of effect you're talking about.
No, but there's still a point to be made. If the wave function immediately after the flash is expressed in terms of something like a Newton-Wigner representation, then there will be superluminal evolution after that, regardless of how you form it to begin with. I think the way Tumulka gets around this is he doesn't use the Newton-Wigner representation, and he uses a representation which I think I would be inclined to say could be argued as not localization in the way we would intuitively want to think about it at all, but nevertheless it can be used for his purposes.
No, I think that's probably right. I mean, and I sort of think that's a strength of the model. You know, it shows you could write down. I mean, people used to sort of just assume that you couldn't fix GRW up to be Lorentz covariant. So people were having all sorts of far out generalizations of GRW and try to generalize those. It turns out you can generalize the plain one to be Lorentz covariant, but of course as physics it's not going to be likely to expect it. I mean, but that's because of those expectations you thought you could do it. So.
Yeah, so Chris's question is very similar to the one that I wanted to ask. I mean, along similar lines, though, how are you going to make sense of, given the fact that the sort of Newton-Wigner localization of the particle is going to spread out past the light cone, how are you going to make sense of the fact that the chance of a flash by that same particle outside the future light cone is zero, right? I mean, wouldn't the Newton-Wigner notion of it being, not just localized within the forward light cone, right? Would that seem to indicate that there could be a flash with non-zero probability outside the forward light cone?
So, I mean, it seems to me that the answer has to be that there's something unphysical about the Newton-Wigner representation. So, you're given this field equation that absent flashes is definitely fine, right? It's a direct equation, and there's nothing. There's no chance of anything going faster than light. And then you mess around with it a bit in a way that's clearly Lorentz covariant to add flashes. And so there's going to be, this story about how we could find out something about the probability of a flash here by finding out where this other flash occurred at space-like distance is telling us, like, it's not, there are collapses, and just like you would have naively thought when you first started thinking about GRW, there's non-locality being introduced by the presence of those flashes. So you really change something in passing from the multi-time Dirac equation to multi-time Dirac equation plus GRW. And that's going to be one, I would imagine that one way in making precise what you've changed is by looking at Newton-Wigner representations of the wave function before the flash and the wave function right after the flash, and noting that something has really changed there.
Right. So let me not then presuppose anything Newton-Wignerish, but I guess I would have. What strikes me as strange is that my initial thought with like if you're doing GRW, and maybe this is just because I'm not very familiar with relativistic versions of GRW, but if you're doing it with like the mass density link or something like that, the tails will still be there out to infinity even after a collapse, and so then the chances of having a collapse anywhere in space, there's no point in space where there's a zero chance of having a collapse there even after a collapse.
That's why these guys weren't interested in generalizing it via changing the rules about mass density.
Right.
About mass density. This is. It turns out you can do it this way, but it's.
So they have different rules for where a collapse will be able to happen than the mass density.
Yeah. Because the mass density guys never managed to hook up a Lorentz invariant model, so. compare. But if they did, I mean, if they cooked up a model set in Minkowski spacetime that they were satisfied with, I believe it would have the kind of features that you're expecting, and then it would be clearly different from this one.
Just a word on behalf of the alternative position, that linear localization is perfectly acceptable. We just need to get used to superluminal evolution and need to only worry about whether the superluminal evolution gives rise to causal anomalies. It's not more clear that it will.
Right. Yeah. So it's not. I mean, it's not that I think there's something amazing that Tumulka achieved by writing down this model, but I don't think the target is amazing that he was able to reach this target that he set himself. But it's not obvious that the target is the right way.
Further questions?
Is this talk why they call you Flash One?
When I was in high school, they called me Flash.
It was my whole reason for giving a talk. I'm so glad.
What is happening physically between the flashes? So there are no flashes.
So when there are no flashes, we've just got these. We've got an n particle system governed by the Dirac equation, and these are just googling along there.
I understand the math. I'm thinking physically.
Physically, well, I mean, if you don't believe, so say there are no flashes, and you think, if you're the kind of person who really likes the wave function, then you think, oh, things are changing all the time, right? But if you're the kind of person who thinks, oh, no, the wave function is just this gnomic kind of thing, then you think, there are no flashes, so nothing's happening, it's really boring. The only change is in the probability distribution over future flashes.
But where's Chester and Wallace?
Well, I mean, Chester, unfortunately, sometimes disappears. So you might become very worried about the problem of walrus identity when there are gaps in his existence. Is that?
So for the number 2 GRW,
Definitely find out towards the past.
maybe strategy, one of the ones where there's no beginning.
Yeah.
So
Yeah.
you say you sort of successively, if that's an epistemic thing, you're successively guessing what the wave function is, or the universe is constructing.
No, it really.
So
it's really. They're all real.
The wave function is a dependent property of the flashes, and it's just is that.
Yeah. Well, I mean, so this is
a dependent function.
Right.
Of the flashes.
So this. Yeah, I mean, this is where it becomes difficult to describe exactly what's going on. Intuitively, if we think the flashes are calling the shots, then the occurrence of the flash made the wave function way back here be this way. But of course, if we just describe how everything is atemporally, it's not obvious. We can read the flashes off from the wave functions, or we can read the wave function. Given one wave function, we can read the rest off from the flashes. So this is like, you might think this in general, that there's a bit of a puzzle why we're positing the flashes as independent existence. If we're just given the wave function history, then we're going to give ourselves enough information to figure out where and when all the collapse events were. And so, why not just say the wave function is all? Right? Why have a primitive ontology at all if you're being a GRW guy when you can recover all that information? This is vigorously resisted by the advocates of the approach, but I couldn't myself. I couldn't on the spot reconstruct these iterations. But a lot of it drives from the feeling that there has to be something that furniture is based on.
Yeah, I mean, just going back to this issue about the Big Bang. I mean, suppose pseudo-Tumulka says this, is what I'd say about Tumulka. Okay, fine, it's not clear what should be said about the theory on full universe. Also, it's not clear what would happen in the Big Bang, because no one knows what would happen in the cataclysmic beginning of the universe. But I've constructed you a quantum theory which has the following developed style features, living on a half section of Minkowski space-time. I mean, we don't actually think space-time in Minkowski. Why do we care about things happening in Minkowski space-time? Assuming we can fit that reasonably well to things happening in localized regions of our universe. Those localized regions tend to have statement that having a satisfactory theory on half of Newhouse space time is in any way foundationally less attractive than having a satisfactory theory on all Newhouse space time.
Yeah. So I mean, this is a kind of interesting feature of this view. Is like you start out thinking that the interpretation you give from quantum mechanics should sort of be independent of whether the past is finite or not. And then it turns out that there are some interpretations that only thrive in the setting where you can get the past to be finite.
But maybe in a sense, I think that's better to me. In a sense, is a falsifiable prediction for thinking. If you
Right.
it's a fairly safe prediction to make.